Welcome to JDR TV on Channel 7. We give you the inside scoop on current sporting events worldwide and connect them to the wonderful world of physics. Today, we are focusing on the physics of the fifth most popular sport around the globe, volleyball.
I'm Jenny Rascon.
And I'm Diana Brown. Today, we're going to look at the powerful sport of volleyball and see if we can spot Newton's 3 laws of motion.
You can see the physics everywhere in volleyball. Let's start with Newton's first law. Diana, tell me again what it is.
It's an object at rest or constant velocity stays at rest or constant velocity unless an unbalanced force acts upon it. For example, during the game of volleyball, after the serve, the ball is at constant motion in one direction until someone, the outside force, hits the ball to move it up in another direction. Let's watch.
That was great. The speed, velocity, acceleration, everything
Whoa!
about that.
No! Stop there, Jenny. Can you help explain those things to me? I always get confused.
Sure, Diana. Speed is the distance traveled divided by the time it takes to travel the distance. Velocity is the speed in a given direction while accelerating in the change in velocity with respect to a change in time.
I think I understand now. So in a volleyball serve,
the ball's velocity stays the same and the acceleration changes as the ball curves up and back down.
so when her serve is too low, it goes into the net, but when it's too high, it hits the ceiling and doesn't go to the net.
Exactly. But enough about that, let's move on to Newton's second law. It says the effect of an unbalanced force is to cause the body to accelerate in the direction of an unbalanced force.
So as we see in the clip, once the force of the bump is applied to the ball, it moves in the same direction that they exerted the force. Also, if you notice, the magnitude of the ball affects where the ball goes.
In volleyball, forces cause acceleration. Let's think about it.
Positive acceleration, bumping, setting, spiking, serving, all causes the ball to accelerate positively. Negative acceleration would be when the ball gets hit into the net and bounces back out, or when the ball is balanced on the top of the net and you don't know which side it's going to fall on.
Moving on to the third law. Since it goes hand in hand, it states for every applied force there is an equal and opposite force. The two forces always act on different objects. For example, every time the ball is hit, no matter how much force you put into it, that's how much hits you back.
During a game, when a player has an action force by spiking the ball, the blocker has a reaction force that is the same.
Jenny, did you know that sometimes in volleyball, forces don't create acceleration?
Is that possible, especially in volleyball?
No, that's stupid. In this clip, there's no acceleration when the ball is already at constant velocity. There's only acceleration when you speed up, slow down, or change direction.
Makes sense now. I think we should end our segment talking about the law of conservation of energy in volleyball. Energy is stored work. When the ball moves in the same direction the force is applied, then that makes it work.
Energy can change from potential to kinetic during a game of volleyball. A ball being held in the air for a serve has more potential energy than it does when it is held at the waist. The player would have less kinetic energy if she stopped moving before she hit the ball with force.
Well, that is all we have time for today. Until next time, I'm Jenny Rascon.
And I'm Diana Brown. This is JDR TV on Channel 7, the only network that lets you see the physics behind your favorite sports.
Join us next time when we talk about Newton's 3 laws in the sport of cheerleading. Merry Christmas and Happy New Year's. Jenny.
Wow!
Santiago Martinez, please come to
Put that in the
Santiago
clip.
Martinez to room 827, please.
Oh, okay.
Oh, 10.
Hey, my name's not Anna.
It's going to be a
Where we at?
challenge to say acceleration. The ball's velocity stays the same and the acceleration... acceleration stays the same and the acceleration changes as the ball curves up and back. I could have sworn there was an L in that. Makes sense now. Makes sense now. Makes sense now. I think makes sense now.
Indeed, it's true.
What are you doing? It feels awkward.
Okay, for us this time.
Okay.